Okay, so we're going to go ahead and get started. So this is about a 20-minute long webinar, and then we will allow for some live Q&A at the end. So if you have any questions during this webinar, please type them in the Q&A box that should be in the bottom right-hand corner of your Zoom window, and we will get to those at the end of the webinar. Here we go.
Thanks, Sam, and thanks to everyone for joining today. My name is Phil Lambert, and I'm the lead customer solutions engineer at Fortify, and I spend a lot of my time supporting our customers and partners on developing new particle-loaded materials with the Flux developer platform on our Flux series of 3D printers. So Fortify is a venture-backed hardware OEM. We design and build 3D printers. The company was spun out of Northeastern University in Boston in 2016. And since then, we've raised over $32 million in funding and have shipped 10 printers to customers across the United States. We're currently located in Boston, Massachusetts, and we've been in our new lab since 2020. So Fortify builds 3D printers, but the Fortify platform also incorporates more than just the hardware. We have some software tools like Compass, which is our build preparation and slicer tool, Fluxos, which is our printer user interface, and Flux Developer, which is something I'll touch on later, which helps folks to onboard novel materials. But the success of our printer is driven by what it can print, and that's where Fortify really sets itself apart. Fortify is positioned at the intersection of additive manufacturing and polymer matrix composites. Almost every material we print is a composite of photopolymer and some type of fiber or particle additive or package of additives. And it's these additives which can introduce a step change in the performance of the final 3D printed DLP part. So Fortify is built on DLP technology. DLP stands for digital light processing. Each printed layer in this process is cured by exposing an image of UV light, which is patterned by the DLP projector. And that DLP projector is the same technology found in overhead projectors in conference rooms and classrooms, except that it's tuned to expose with UV light. So our printers have a competitive build envelope of 8 inches by 4.5 inches by 13 inches, with excellent pixel resolution and a wide range of achievable layer thicknesses. But what really sets our system apart is our rugged design, the ability to get a lot of force through that build plate and into the resin. It's tuned to print really tough to process photopolymer material systems. Beyond that, we have an onboard tool set called CKM, or Continuous Kinetic Mixing. This is our module that mixes, heats, and recirculates fiber-filled resins. By both heating and mixing, we're able to take advantage of viscosity reduction introduced via heat, while also managing the homogeneity of the heterogeneous material system through simultaneous mixing. So that means mixing and heating and recirculation keep fibers and particles in suspension. And this is integrated into all of the Flux series printers. With CKM, we're able to expand our processing windows into areas where other DLP systems cannot compete. So if you look at this chart on the left, as the sedimentation rate goes up or the viscosity increases, the processing envelope grows beyond where other DLP printers can print. That means we're able to process materials with higher settling rates, higher viscosities, and typically this means higher loadings of fibers and particle additives that are the aspect of these materials that are creating a real step change in behavior or material performance. Now that brings on Flux Developer. Our material partners are imperative for developing and onboarding new and novel material systems to our printer platform. Partners like Tethon, who we will hear from in a little bit, are taking advantage of our Flux Developer toolsets to do their own materials development and bring novel materials to the Fortify Flux series printer. So Flux Developer is a software product, and it enables new material development. When onboarding a new material, typically our customer or partner have material formulations in mind. And they need to see if they, on a very basic level, are curable, photo-curable. So we have some onboarding experiments that live on the machine that our customers can leverage to do some initial product screening and characterization of their material. Once they have an understanding of their material at a deeper level, they can create a materials profile. We have some tool sets for that. With a material profile created, they can run a print, analyze the results, and then there are some feedback loops here. You can either go back to materials formulation and start the whole process over again, or more likely, go back and run more onboarding experiments or tune your materials configuration. So with Flux Developer, you can run through this workflow a few different ways using a few different tools. As I mentioned earlier, the tools on the machine include the photokinetics analysis and the build plate adhesion test. So these two tools live directly in the user interface on Flux host, and they can be run and configured to test a wide variety of parameters. For the photokinetics analysis, you can do some tests that figure out how a specific material system responds to dosage and intensity of the UV light. And in the build plate adhesion test, you can study how the printed material adheres to the build plate. There are more tools to Flux Developer. We also have the web app, which is a browser-based interface where our users can create, store, and share material configurations within an organization, and also activate and retire specific material configurations, letting our customers choose which configurations are active and available on the printer, or retired because they've been replaced by something more relevant or a configuration that's been updated. It's in this material configuration creation tool that our customers can adjust peel settings like peel speed and layer thickness, and other things like UV intensity and UV dosage for every layer. Once a configuration has been created and has been activated, that material configuration is available on FluxHost, which is, again, the user interface on the printer. When those configurations are activated, the user can select from those activated configurations to print with their material. Coming soon to Flux Developer are a bunch of history and analytics tools. So our customers will very soon be able to track experimental variables across prints, tie configurations, consumables, resin batch, resin type, and more to each print job. And then every organization and printer and job will have more data tied to it. Things like build time, number of layers, build name, build date, and then unique identifiers for every single build. So these tools will help our customers to track their experiments and have a good understanding of success and failure related to each experiment, related to each build, and have a really complete history of their onboarding efforts. So that was a high-level introduction of Flux Developer. And there's a lot more to it, but what better way to learn about the power of Flux Developer than to hear directly from a user? Now I'd like to hand the presentation over to Trent Allen from our materials partner at Tethon 3D. He will discuss how the Fortify FluxCore printer is used in combination with Flux Developer to onboard and print their high-performance ceramic materials.
Thank you, Phil, for the introduction, and thanks to the team at Fortify for putting together this webinar. For those of you who aren't familiar with Tethon, I'd first like to offer a little background about our company. Tethon 3D is a privately held company headquartered in beautiful Omaha, Nebraska. You can see our office building right there. Our original IP was actually spun out of Bowling Green State University, based around ceramic additive binder jetting. Our company was founded by Dr. James and Karen Linder in 2014, and we more recently entered the UV curables market in 2016. Today, we currently have 10 employees who mainly focus on developing materials for binder jetting and UV processes. Tethon has over 1,300 customers in over 40 countries who have purchased our materials to print on binder jetting or UV hardware. For today's webinar, we are going to dig in a little deeper into ceramic materials and how our team is currently using the Fortify Flux machine to move ceramic additive from prototyping to production. First, I want to go over the workflow in case some listeners aren't familiar with the additive process or ceramics in general. Our team first takes a digital file that has been designed from the slicer software, and then we upload it onto the Flux machine. We then pour in a UV resin that has been manufactured by Tethon here in Omaha. In this state, the material is a ceramic composite made up of ceramic particles and photopolymer resin. We then begin printing the file on the Flux. After printing the object via DLP layers, we then clean the part and bison wash or IPA to remove any excess resin. Unlike most UV resins, we do not post-cure the parts. However, we then take the part and do a one-step debinding and centering process. Depending on the material we are printing, will determine the amount of time for the centering process, but generally speaking, it is around a 16 to 24 hour turnaround. During the process, the polymers burn out in a centering furnace, and the remaining ceramic particles are vitrified to create a true ceramic object. So on this slide, you can see the green objects there on the top right, and then the centered object is there on the bottom right. So you can print ceramics. That's great, but why do you want to do that? You know, the majority of our customers are printing ceramics due to their operating temperatures. Where polymers will begin to melt and metals may warp, ceramics can generally be used at higher temperatures. So on this slide, you can see a range of some of the materials we sell at Tethon, just going from our base resin up to a high purity alumina material. Due to high temperature properties, our ceramics are used extensively in the defense, oil and gas, electronics, aerospace, and even outer space industries. But there are also many other applications for ceramics in the dental, health, and design industries that may use ceramics for their inert, food safe, or sustainability properties. So why is our team at Tethon so excited about this partnership with Fortify? Our materials have been printed with dozens of SLA, DLP, clip, and LCD technologies. I know Phil went over the Fortify Flux core technology, so I don't want to dig in too deep on this, but together this partnership will enable the highest throughput when it comes to ceramic additive. Outside of having the largest build volume for ceramic DLP printing, the Flux is also able to process materials no other hardware solutions can. As a materials company focused on developing next generation solutions for our customers, we use the Flux to stay on the cutting edge of material innovation. While our materials may be limited by some hardware and closed system, the Flux is really a tool that helps us level up. So in the video, you can see the viscosity of the resins that we are using on the Fortify Flux machine. Most printers would not be able to handle this type of material. So what materials have we developed for the Flux today? So far, we've launched 2 materials for the Flux machines. The first is LSAS, which stands for low shrink aluminum silicate. This material is a mid-grade alumina ceramic material that centers at 1250 C. This material can be fired in a low-cost pottery kiln at cone 7. This LSAS material shrinks less than 5% and is isotropic in nature. This is really unheard of in the ceramic additive industry and is the only material of its kind. But why does this matter? The more a part shrinks, the more likely you'll see warpage and be unable to hit necessary tolerances. Due to having higher ceramic loading, you will also be able to print thicker walls, not need to scale up as much, and also use less material. We've developed the ceramic material to actually shrink less than traditional manufacturing of ceramics, and that's very exciting. So how do we do it? A lot of it goes into our ability to load the UV resins with powders. Currently, all of our materials are loaded at least 10% higher by volume than any competing similar materials on the market. This matters a lot. When you look at scaling, creating big parts, and moving into production, you can't have parts shrinking 20%. So, what applications is this LSAS material good for? While ceramics don't have great tensile strength, they are very strong in compressive strength. If you have an application that needs to withstand temperatures between 300 C and 1300 C, this material won't flinch at all. While not fully dense, this material can be used for a lot of applications in the oil and gas, electronics, and automotive industries. Going back to shrinkage and how, not fun it is, we've seen this material used a lot for setters and fixtures. There are many issues with MIM parts warping, and even significantly more issues when you look at metal binder jetted parts warping. This material is great to be used as a setter, sacrificial part, or waster plate for other metal objects. If you're getting started in ceramic additive, this is the material to start with, as it has material properties that cover a large swath of applications and parts. The second material we've designed for the Flux core is HPA, which stands for high purity alumina. This material is over 99.8% pure alumina post-sintering. Once again, this material is loaded much higher than any competing similar materials on the market, and you'll see under 13% shrinkage during the sintering process. Within traditional ceramics, you will find most aluminas will shrink around 12%. As you can see, we are now hitting industry standards with our materials. So how does this material differentiate from the LSAS material? This HPA material would be considered a more technical ceramic. This material sinters at 1700 C, has great thermal shock properties, and will be fully dense at that temperature. Also, with the type of purity at over 99.5%, it can be used more within the electronics and semiconductor industries due to its anti-corrosive properties. For those in the defense and aerospace industry, this material can be a great alternative to working with some carbides or costly zirconia materials. The LSAS and HPA materials are very popular materials in the ceramic additive space. However, the teams at Fortify and Tethon are working in conjunction to bring more materials to this space. Our team at Tethon has a vast experience developing a wide variety of oxides, nitrides, and carbides. While there are some other off-the-shelf ceramics on our roadmap, I wanted to talk briefly about the other half of our business at Tethon, which is custom material development. Tethon has a wide variety of base resins we use when adding different fillers. As part of this, we have a lot of customers who will send us powders to see if they can be printed. This includes many different types of oxides, nitrides, carbides, metals, and other type of filler materials. One common way a material previously didn't pass our feasibility study was the inability for the powder to stay suspended. If a material will only stay in suspension for a couple hours, it's not terribly useful if you need to move into production. This is really where the continuous kinetic mixing on the Fortify Flux core is so great. There's no longer the need to worry about our particles settling at the bottom of the vat. It just takes one extra thing away from being able to develop a new material. Also, the other reason most materials have failed to date is due to low loading. With lower loading, you once again will have shrinkage, consistency, density, and centering issues. While most plastic hardware will limit loading due to viscosity issues, the Flux core can handle extremely viscous resins, as I mentioned before, and it has an extremely powerful Z-axis to help with printing these materials. Matched with Tethon's experience to create shear thinning materials, we can help your firm process new materials that weren't previously possible. Our team is very interested in developing more hard to process materials like nitrides, carbides, cermets, and metals. If this seems like something you may be interested in, don't hesitate to reach out to Phil or myself. Thank you.
Thanks, Trent, for that excellent explanation of how your team leveraged Flux Developer and the Flux Core 3D printer to develop two excellent low shrink, high performance ceramic materials. If you want to print large parts with great resolution and low shrinkage, reach out to Trent or myself. I've left our contact information on this slide. Thanks again, Trent. Thanks again to everybody who joined us today. Looking forward to the next webinar.
Thanks, guys, for putting that together. I really appreciate it. So now it's time for some Q&A. So one of the first questions we got is Fortify material for specific equipment only?
Yeah, so I can go ahead and answer that. The materials Tethon has developed, the two materials that I went over in the presentation, are designed specifically for the Fortify Flux machines.
Great, thank you. What is the maximum wall thickness you can achieve?
Yeah, so with that low shrinkage material, the LSAS, we are able to do walls over 1 centimeter in thickness. So compared to, if you're familiar with some other ceramic additive solutions in the space, we are able to do much thicker walls. And a lot of that has to do with the amount we are able to load the resins with powder, and then just the limited shrinkage.
Thank you. And what is the repeatability of the shrink rate?
Yeah, that's a great question. For us, it's repeatable every single time, right? So, it can change depending based on the geometry of the part. You could see slightly different shrinkage, but as you move into production from part to part to part, that shrinkage is going to be the exact same every time. So it might take you 1 or 2 times to figure out the shrinkage based on that geometry, but over the long run, it's very consistent over and over.
Okay. What are the maximum solid loading of the Tethon resins?
Yeah. So that's a great question as well. It is going to be highly dependent on the powders you're working with, right? So like for these two materials, they're an alumina base. We're going to be able to achieve higher loadings with that than maybe say a carbide material or a zirconia material. And so I can't give you an exact percentage. I will say we've got some materials loaded up to above 90% by weight and above 75% by volume. And so for us, it really is material dependent. So depending on what type of alumina or ceramic or metal material, it's going to make a huge difference on what loadings you can achieve.
All right. So we're getting some questions here. What is the smallest possible feature, like minimum wall thickness, smallest possible hole diameter, etc.?
Mm-hmm. So, Phil, do you know for your Flux machine, what that would be, your smallest features that you're able to print?
Yeah, it's an interesting question because there is a hardware component to it and a materials component to it. Mm-hmm. On the hardware, the layer thicknesses can go down to 25, 35 microns, depending on the material, and then up to a millimeter, providing that you can cure that deep. On the feature size, the cross-sectional pixel size is 75 microns. but there are practical limits that are quite a bit higher than that when you go to specific materials. I'm not sure for the HPA or the low shrink aluminosilicate what the minimum feature sizes are, because I haven't pushed those myself. Do you have a little bit more information around that, Trent? I think the wall thicknesses are 5 millimeters in the largest, and about I don't know, I'm not sure if the low end is.
Yeah, so that would be something I need to look up to get those exact figures. But yeah, as far as the wall thickness, with the LSAS, we should be able to get up over 1 centimeter. So I would need to look up the kind of the minimum feature size. We do print a lot of parts, so I can definitely find out that information.
Yeah, we are printing those materials at 50 microns, and sorry, 50 micron layers.
All right. Let's see here. Can you talk a little bit about circumstances where printed pieces can be used green?
That's an interesting question. For the ceramic materials, there's perhaps some radio frequency applications where the material could be used green and the requirements aren't necessarily mechanical in nature. I think there are certainly some applications there. There's some dependency related to the RF performance, the green body. That has not been characterized yet by us, but perhaps some applications in that space.
Yeah. And I would say, you know, from our perspective, we really design the materials to be centered, but they can be used in the green state. You know, you could add ceramic fillers just to add strength to your normal photopolymers. And as Phil mentioned, you know, there are some mechanical properties and other dielectric properties where actually having it in the green state could be beneficial. So while we kind of focus on the centered part, there certainly are applications that would utilize our materials in the green state.
All right. So what prevents the printing of thick walls? Why is there a maximum wall thickness?
Yeah, so that's a great question. So with ceramic additive, we are needing to burn out that photopolymer resin out of the matrix. And so to have the photopolymer escape during that debinding, you're not allowed to kind of have as thick walls because that resin needs to kind of escape during that process. And so with most ceramic additive, you might see, you know, really tiny parts that, you know, might only have 1 millimeter or two millimeter wall thicknesses. You know, we're going to keep increasing our ability to print thicker parts, but it definitely is a challenge with ceramic additive today. But it, you know, over the next few years, we can kind of overcome that and keep kind of pushing the limits of what's possible.
All right. And would you expect distortion in tiny structures like Eiffel Tower?
Yeah, it's definitely potentially could be a concern. If you ever have any questions over a file, you know, we can always take a look and let you know how well that file is going to translate over to ceramic AM. You know, the biggest thing is by limiting, you know, I keep going back to it, but limiting the amount of shrinkage, you're going to limit the amount of warpage. So by being able to load these materials as high as possible with powder, you'll certainly see less warpage and less shrinkage than you're used to in the ceramic AM industry.
All right. We're getting a lot of questions here. Okay. What are some of the defects you see during burning the green parts, and how do you avoid it?
Yeah, so the biggest issues would be laminar cracking. So if you see cracks on the parts around, you know, layer lines, you may see some warpage. Those are also concerns. But really, you know, we focus a lot here at Tethon on our centering cycles to figure out how to properly center these materials. We also, you know, as part of that, we focus on a kind of one-step debinding. So we burn out the polymer, and then kind of keep that process going to fully center that material. So by doing that, you're going to actually limit the amount of cracks you could potentially see, the warpage you can see, by keeping that part heated instead of bringing it and dropping it back down to cool. So there are, some potential issues with centering ceramic parts, but those are things we work on every day to kind of get past, so that we don't have to worry about any type of warpage or cracking or anything like that.
Okay. What is the minimum resin amount required? Can it be recycled from the tray?
Yeah, so it seems with this material, around 300 milliliters is the right amount to get started. We typically suggest a little bit more than that so that you can make sure that you have longevity in your builds. And the resin certainly is recyclable, can be recovered and reconstituted, reintroduced back into the reservoir for printing again. Anything you want to add there, Trent?
Yeah, that's exactly right. So,
cool.
And are there any plans for using dark, high refractive index powders?
I would say for us, it's definitely on our roadmap. We've done a lot of work in the defense industry, working with different carbides, and we've taken a lot of that technology from those projects, and we really believe that will help us develop some kind of next generation, darker, higher refractive materials, like even zirconia. While it's not dark, it is highly refractive. There's a lot of technology we're able to kind of push forward based off of some stuff we've worked on in the past. So those are the type of materials we see a lot of value in the Flux, right? Some of those materials are extremely hard to cure. And, we didn't mention this during the webinar, but the Flux system and having the ability to change the light intensity and kind of optimize it based on the powder itself. The Flux machine has an extremely powerful projector. It's really going to help us kind of push what's possible. So in the past, where some of those materials simply weren't possible on most SLA or DLP systems, we're going to be able to move into some more unique materials going forward.
Great. We're still getting some more questions. So I think we have time for one or two more. If we didn't get to your question and you would still like to have it answered, go ahead and send us an email. I will put it in the chat here to everyone what your guys' emails are, so they can just email you directly. So how about, let's see here. I think maybe we just need a little bit more clarity on the materials. Are they made just for Flux printer?
Yeah. So these materials, the two during the webinar, are designed specifically for the Flux machine. At Tethon, we do have a line of bison resins we actually sell for our bison printer, and then we have a line of universal resins. The biggest difference between kind of our universal resins and the Fortify resins is going to be that our Fortify resins are loaded much higher with powder. They're much lower shrinkage, and they're just more technical in ceramic nature. So the Fortify resins we're able to optimize because we have a Fortify printer in-house, where some of our universal resins, we really just made it so they're able to be printed on kind of a wide variety of SLA DLP printers. And so it's just kind of a different quality of material. But yeah, as far as the materials during this webinar, they're all designed for the Flux machine.
Yeah, it's also worth noting that those materials, when you buy a Flux core machine, the configurations that control those materials, the amount of energy, intensity, the peel and plunge rates, everything that you can control with Flux Developer has been predefined for those materials, so that when you buy the material and the machine, you'll have the ability to print that material immediately, and you won't have to solve those problems for yourself.
Awesome. I think we can go ahead and end that here. I did put in the email in the chat for everyone. If you have any additional questions or we didn't have time to get to yours. Just so everyone knows, we will be, this is recorded and it's going to go up on our YouTube channel later today. And everyone on this webinar will get an email from Fortify with a link to that YouTube channel, so you can share the webinar with any of your colleagues or anyone else who might be interested. I do want to thank Phil and Trent for your guys' time on this. I really appreciate it. And thank you to everyone who took the time to watch this webinar. Happy holidays, everyone.
Thanks, Sam.
Thank you.
Bye.